Welcome to the 58th lecture of surface engineering. We are now discussing in the last few lectures about how to utilize laser for surface modification. Initially, we talked about only microstructural changes, namely say hardening or surface melting and so on. And then we also picked up examples of cases where we modified the composition as well. So one of the example was called surface alloying, where we use the incident laser beam as a clean non-contact source of heating, and by way of either feeding alloying elements or pre-placing certain layers of alloying elements, we could modify the microstructure and composition both. And we did see that certain improvements in terms of surface dependent properties are possible by this approach. So in case of laser surface alloying, the change in composition is graded. The top surface probably will have the highest concentration of alloying elements, and near the solid substrate, the coating substrate interface, the concentration of the alloying elements usually is the minimum. So you see a maximum concentration to minimum concentration across the alloyed zone. In case of certain applications where we want a very different composition to be overlaid, just like we do weld overlay. So we are now going to discuss a process called laser surface cladding, which is nothing but another approach of laser assisted surface engineering or laser surface engineering. And in this, we actually will actually discuss the process which will make us allow us to change both the composition and the microstructure. So this is laser surface cladding. Now we can do in either of the two possibilities, just like any other laser processing. We can use pulses of laser in quick bursts of certain frequency with a certain pulse width. So that's one way of doing that, but that's also very useful in certain applications, but generally the more common and the more popular method is continuous wave. And when the laser is actually irradiated in a continuous wave, and the alloying elements, or so to say the clad elements or clad mixture, is fed in the form of a wire. So you actually have to prepare a powder feed and then compact that and extrude that in the form of a wire or a rod, and then you feed into the system. So for example, as you are seeing here, from the top you are feeding the laser beam, and sidewise laterally you are feeding a wire or a rod, which actually has a composition very different than the substrate. So the very basic or the fundamentals of the approach wise, if this is the substrate, now in case of alloying, we actually had a pre-placed layer or a simultaneously fade layer, and then we allowed the laser beam to raster over, scan over, and then create an alloyed zone. In case of cladding, what we create is possibly a thicker layer, but the most important part is this clad will have a composition very different than the substrate. So in terms of composition profile, let's say we are talking in terms of a particular element B, in terms of the depth as a function of depth into the substrate. So in case of alloying, we expect a profile which is diffused like that. So this is in case of laser surface alloying. In case of cladding, we may have a composition profile which will be very drastically very different. So we'll have a rather sharp interface, and this would mean that this region, the so-called clad region, will have a completely different alloy altogether. So obviously the interface being sharp, the immediate concern could be about the integration or adherence to the underlying substrate. But the advantage in case of laser cladding, in case of laser surface cladding, is that when we overlay this molten layer, the molten layer, because it is in the molten state, is at a much higher temperature. So invariably in contact with the substrate, it will dissolve or melt a portion of the substrate and the interface that we are talking about. So this interface is not entirely devoid of intermixing. So the clad will have certain amount of intermixing with the underlying substrate. And as a result, the interface, though is fairly sharp, but will have good metallurgical bonding. In other words, the adherence is not a major concern in surface cladding. So what we do is we can feed in the form of a wire or rod or some other form, and we expect that feed to be melted and fused to the underlying substrate. And since this is a continuous wave process, here we can expect a much thicker and a much faster process of cladding than what is possible in case of pulse deposition. So continuous wave cladding actually kinetically is faster and also is more convenient to make a thicker coating. So as I said, we actually will create a molten pool, and the molten pool, and in that will feed the filler wire, and the wire is melted and incorporated, and we have very nice bonding, metallurgical bonding, and the whole process can be completely automated. So essentially, for a certain surface area coverage, if this is the area that we want to cover, so we'll have said this is depending on the size of the melt pool and the beam size. If this is the first clad layer, then the next layer will be here with a certain amount of overlap, just like in case of any other laser process. So this is how we'll actually create overlapping layers, and then eventually we'll cover the whole surface. The whole process can be automated with a motion like this, and in the process we'll cover the whole surface. So this is the top view, but in terms of front view, when we create this thick layer, this layer can be fairly thick compared to alloyed zone. We can actually think of creating a similar clad by feeding powder. So we can have a situation where this is the way we are feeding the beam. This is the beam which is actually creating an overlay on top of the circular section, the tube, and we can have multiple nozzles, and this is the way the laser beam is irradiating, but we can have multiple nozzles which can feed powder into the zone, and so this is the zone in which the powder is flowing. And so these nozzles could be actually could be subtending a certain angle so that the feed creates a bigger, or the focus plume here, but we can also have a crossover earlier in case we are feeding through coaxial nozzle. That means this is the opening for the laser to pass, laser to fall, to irradiate, and we can have a concentric hole which is just surrounding the laser beam, and through this we can feed the powder. So by the time the beam hits the substrate here, the powder also will be molten in contact with the laser beam and create a clad on top of this. So what is important is we have to control the beam fluence, of course the power density and the point of focus and so on. Then also the interaction time by way of controlling the speed, relative speed between the two. Then we also take care of the powder stream, and the biggest advantage in case of cladding is we can actually feed a powder mix, which this mix actually may have not just A, it can have A, B, or maybe certain compounds like A to B and so on. So that means it is up to us what kind of applications we have in mind, and we mix the powder and then either feed the powder mix directly, or we can have multiple hoppers and we can feed these powders as different through different nozzles. So both are possible. The best option to make very uniform clad is to mix them and then fuse them in the form of a wire or of other kind of feed, and then directly feed along with the laser beam. The relative movement of the workpiece with respect to the laser, either the beam is moving or the workpiece or the stage is moving. Either way, we create a relative motion, and that will actually be determine what is the interaction time, and this interaction time, apart from the power density, are the two process parameters, just like any other laser material processing. The thickness that we build can be built to a higher degree to the height of the clad zone, or the bead that we create may be controlled and may be built to much higher vertical height by way of making multiple layers. So we actually can create multiple layers and then make a vertically a layer thickness. We can increase the layer thickness to a reasonably high level. This was about thick coating. We can also create similar clad layers by way of pulse deposition. So here the delivery mode is, the laser irradiation mode is pulsed. So here we will have a particular substrate. So this is the substrate and this is the target, which can be a target of desired composition. So we can premix powders or other feed and then create an alloy here, which can be very different than a conventional alloy. So in other words, the composition of these target can be completely tailored the way we want, and we use a laser beam which will hit this target and immediately vaporize a part of it, and those vapor will travel through this particular distance, and by the time it reaches the substrate, it actually undergoes a change of state and then either condense directly from the vapor or condense in the form of semi-molten splats. Now this is how we actually can also create a clad layer, but that thickness of that clad layer will be fairly small. So here we may use this either for semiconductor applications, various device applications where we need a very thin layer, or even in metallurgical applications we can use this as a final layer which can close the pores and other defects onto the surface and create a thin layer of a very different and a matching composition. Now, just like the previous few examples, I'm now going to take up a few examples from the published results from our own group at IIT Kharagpur. The first example is about trying to clad bulk metallic glass. Now, we all are aware that metallic elements, when we routinely use them in any form at room temperature, we expect 99.9% of them to manifest in the crystalline form. So in general, metals are crystalline, and metallic alloys also are almost every time is a crystalline metal. But then under certain non-equilibrium processing conditions like rapid solidification or high energy milling or high angular axial pressing and so on, we can actually destroy the usual or equilibrium structure, the crystallinity, and then retain a liquid-like structure which we call amorphous, and a subset of that could be a glassy material. So bulk metallic glass is a specially made alloy which, when cooled not necessarily under very rapid cooling condition, unlike splat cooling where the solidification velocity could be 10 raised to 4 to 5 Kelvin per second, even with a few hundred degrees per second cooling rate. So typically what you experience when you cast a metal onto a metal mold, so a molten metal cast into a metal mold easily will undergo few hundred degrees per second of few tens of degrees per second, up to about few hundred degrees per second of the quenching rate. Even in that, we are able to, if we are able to retain a liquid-like structure which is amorphous, then we call it a bulk metallic glass. So essentially the critical cooling rate that we need to employ for these set of alloys is relatively slow, and yet we are able to retain the amorphous structure just like in the molten state. So these bulk metallic glass, one particular composition with certain metalloids like boron and carbon, along with a rare earth of yttrium and then iron, chromium, molybdenum. So mixture of these is known to be a good glass forming composition. So this is the signature that at room temperature, when you cast this alloy, this typical composition, and atomize them in the form of this powder, the powder shows completely hollow and is completely devoid of any crystalline peak. So this is completely amorphous. So the idea was that if you have a steel substrate, and if this steel substrate is coated with such bulk metallic glass, then you are completely covering up the polycrystalline aggregate with an amorphous layer. Now, we are aware that in any microstructure, when you have such polycrystalline aggregate, usually the boundaries contain more defects and act as anodic compared to the core of the grain. So we always will have, typically this is the boundary and this is the core, we always will see a galvanic cell created between the center of the crystal to the surface of the crystal. And this is the reason why steel, for example, or for that matter most of the polycrystalline metals are prone to corrosion attack at room temperature. Now if you can cover this up with a layer which is completely devoid of these boundaries, that means when you have a bulk metallic glass, then obviously you are talking only compositional variation or domains, but there is no crystallinity, there is no grain and grain boundary structure. So in such a situation you are likely to see a complete, you may expect that there will be no corrosion at all. So with this idea we actually overlaid this kind of a bulk metallic glass using laser beam and created a clad surface on top of a bearing steel. And to our surprise, what we found that no matter how we change the process parameters, either single or double seam or various combinations of power and scan speed, but every time we end up getting certain crystalline peaks. In other words, that we were unable to retain a complete metallic glass or amorphous structure after laser cladding. And the reason is very simple, that when you have elements on one hand like iron, chromium, molybdenum, and on the other hand you have metalloids like carbon and boron, so they have very different melting temperatures, very different densities, very different specific heats, and most importantly they have very different tendencies of formation of clusters. So under forced cooling we were able to retain this entire composition as a single phase, but when we clad, whatever little time we allow for the melt to experience or allow solute partitioning, within those few tens of milliseconds or microseconds, it was enough for the elements like boron, carbon to segregate away from iron, chromium and so on, and in the process easily they could form these borides or carbides or various forms of interstitial compounds. And as a result, once you allow this solute segregation, then those phases emerge from the liquid, and once the composition is violated from this uniform composition, then obviously the glass transition temperature or the glass forming ability decreases, and by the time the liquid solidifies, you no longer have a composition which can stabilize the amorphous structure of the liquid, but instead it allows multiple crystallization of these phases, and the remnant liquid also crystallizes in the form of a matrix solid. So we are enabled to, but so typically this is on the cross section, this is the kind of a clad layer thickness that you develop. On top of that there will be a heat affected zone, but in this heat affected zone obviously there will be some amount of intermixing. So this is the substrate, this is the heat affected zone, and this is the clad layer, and a very little area where you will have some intermixing in the semi-molten state. So if you look at this microstructure of this clad zone, you see these kind of dendritic pattern of solidification, which simply shows that there must have been solute segregation, and because of which you actually form these primary phases, and in interdendritic spaces you have multiple compounds like those borides and carbides precipitating out. So on the top view, this is the kind of views you have. So these bright regions, white regions, are typically the interstitial or interstitial compounds that are formed, and they have decorated these boundaries in between. So this is the primary solid. When it grows, so there are multiple such primary solid nucleating growing together and staging a competition. And during such growth, the spaces in between such columnar grains or the dendritic arms, you have the remnant liquids eventually solidifying in the form of multiple mixtures. In fact, it can be a eutectic, it can be just several compounds precipitating out of the liquid. So this is also borne out by this kind of a phase diagram. So the take home message is that you do create a very, you can create a very thick layer, a clad layer, very well integrated with the substrate, but there's no necessity that even with the cooling rate that you can employ with the laser surface cladding process, easily 10⁻³ Kelvin per second or higher, even then you are not able to retain the entire glassy matrix or the amorphous matrix. Now, this kind of an approach can be more useful. So that was an exploratory approach where we wanted to retain amorphous structure of the liquid state into the solid, but that wasn't possible. But nevertheless, I didn't present the remaining part of the results, which shows very significant improvement in hardness and wear resistance of that layer. But here we are talking about a different example where, for example, imagine a particular tool, maybe a roll or a shear blade or some other manufacturing device, because of certain working conditions undergoes heavy amount of wear. So if the whole component is very expensive, then you don't feel like throwing it away and then replacing overnight. The manufacturer always would like to retain and reuse it as far as possible. So that is when you go for reclamation or repair job. And we did discuss in the earlier sections something called weld overlay. So where you actually use a welding torch and a filler metal to create an overlay on top of the tool or the solid substrate, and then try to restore the dimensional, whatever dimension you had before. So, but in order to restore the dimension, we used a material usually in the form of filler rod, which is very different in composition than the base substrate. But laser surface cladding allows you to actually create an overlay for dimensional restoration or repair or refurbishment with the same composition. That means there'll be hardly any sharp interface created at all, and there'll be no question in terms of extra stresses created at the interface. So here is a cross section of such a clad. The compositionally, both the substrate and the clad has the same composition, H13 tool steel. And this tool steel, we were able to actually create a clad. For example, these are seams which are parallel ones, very neatly done parallel seams. So if you create such clad beads along a certain direction with certain level of overlap, then what actually was done in this case was not only to look at the cross section and so on, so very nice bonding with the base substrate, but from this top layer we were also able to extract samples for tensile testing, which is along the clad direction or across the clad direction. That means in the longitudinal and transverse direction both, because this clad thickness was sufficient for machining out these small specimens. Now, what is really significant in this whole case is that we had very good mechanical properties and so on, but what is very interesting is that the microstructure that you develop in the clad zone also is martensitic in nature. Now, normally in case of plain carbon steel or normal alloy steel, when you melt and solidify, you don't necessarily get martensite, because you go through the liquid to solid transition, and that's when austenite forms, and in most of the cases austenite is retained during the fast cooling process until room temperature. You may form certain other phases, but in order to get martensite, we are aware that we must avoid occurrence of any diffusional transformation. So if you just quickly recall, if this is the temperature and this is the time axis, so we are referring to a continuous cooling curve like this, and our cooling rate all the way must be very fast, and we should be able to avoid intersecting any of these pearlite start or pearlite finish curves. Now, usually this is a solid state process, but when you start cooling all the way from liquid state, so here is your liquidus line, so you start all the way from liquid state to be able to avoid altogether and then reach room temperature after crossing the martensite start. This is not very commonplace. But in this case, in this kind of a situation, because the bulk of the substrate acts as a heat sink and extracts heat very fast. So the cooling all the way from the liquid state to room temperature in this particular case allowed formation of not only the solid but solid in the form of shear transformation product or martensite. So when we carried out these mechanical tests, and by the by, along with martensite, there were also plenty of carbides formed during this cooling process. So very fine carbides in between the laths, martensitic lath, created a very good mechanical property. And as I said, we actually extracted machined out microtensile specimens both along longitudinal and transverse directions. And when we carried out the tensile tests, to our surprise, what we found that if one is the situation of mechanical testing result in case of hardened and tempered condition, in case after laser clad, we were able to reach much higher strength, much higher yield strength, and after not only clad but cladding plus some tempering or annealing treatment, we were able to get fairly higher, still higher strength, but a much higher range of ductility, much higher deformability. So you are able to actually combine both higher strength and toughness in the material which is overlaid or clad. So laser surface cladding then gives me a possibility where actually one is able to reach very high strength, very high yield strength and UTS both, and also retain 7 or 8% of ductility, which is a very good news. In fact, in a way, this layer could be better in terms of mechanical integrity and property than the original cast product. So similar approaches can be obtained, say, for creating certain graded composites onto the surface. So here is an example. These are automobile components which can be eventually made out of magnesium, certainly not steel, not titanium, not even aluminum. We are talking about magnesium, so obviously density wise much lower, and then the overall weight reduction will be significant. But magnesium is very prone to oxidation, corrosion, and also carries fairly low strength and poor wear resistance. So in order to introduce a good amount of wear resistance, so what is possible is by way of laser cladding, you actually create a composite surface. So you clad a powder which is a mixture of matrix phase, which could be magnesium or magnesium aluminum mixture, along with that certain carbides, in this case silicon carbide. So you can select the required type of carbides, mix them, and then when you clad, you actually, if this is the substrate, the first layer, the second layer, the third layer, so you create different layers, and as you go on top, you can change the amount of these carbides gradually. So at the bottom layer, you can have low volume fraction of carbides and higher amount of matrix metallic phases, so that the bonding here is better, more metallic bonding, metallurgical bonding. But then on top layer, you can have a higher volume fraction of these carbides. So on the cross section, you see very nice wetting and a composite layer created on top. So on a metallic substrate and alloy, I can create a composite layer, and that too with graded composition by way of laser cladding. So this was possible with earlier one was with a particular magnesium alloy, and this is pure magnesium with silicon carbide, similar composite layer created with certain amount of good wetting and so on. And as a result, one can create a very high hardness level, almost twice or three times than the base hardness level, and see a very well wetting of the carbides, forming certain reaction layers around them. One can do a similar thing with aluminum. Here the composite layer is the matrix is aluminum and the dispersoids are the silicon carbides, and you create such microstructures which is very well practically defect free and can be fairly thick, which is not possible in case of other materials. And another good thing is that when you create such a layer, you actually have very nice, there will be certain eutectic formation in the interdendritic spaces, but these are the regions which is very good in terms of offering high wear resistance and hardness. Now, laser also allows you to create a very exotic combination of phases, a boride and a nitride, created on the same surface by the same operation. So you start with certain boron nitride powder mixed with titanium alloy powder, and then spread it with some binder like PVC, PVA, and then you create a thick layer, pre-pressed layer, and then use a laser beam to scan over it. And in the process, you do see certain reactions which allows you to form both boride and nitride, a composite layer comprising both boride and nitride of titanium by the same operation. And in fact, you can use different energy densities, and as a result, you can see, so this is with 5 boron nitride, and this is with 15 weight% boron nitride addition. And as a result, of course, the Young's modulus would be higher in one of these two cases where you have higher amount of boron nitride. You can also see variation in hardness, variation in wear rate, and you can easily figure out that with 5-8% of boron nitride, you actually can create a wear resistance level which is fairly comparable to substrate which is much harder. So one can also alloy silicon carbide on titanium. So I showed you examples of magnesium, magnesium alloy, aluminum, and now silicon carbide on titanium, pure titanium. So here again you create an exotic microstructure where you have these silicide layers formed along with a eutectic of finely dispersed phases. So this kind of a microstructure actually can make you can give you much better mechanical properties, and the fineness of the microstructure of the clad zone can be easily controlled by controlling these typical laser parameters as power and the scan speed. And depending on the depending on the level of or the combination of these two major process parameters, you can vary the microstructure and even composition to a significant level. So we have now completed the discussion in terms of changing the composition by way of alloying and now cladding. So cladding gives us an advantage that in case we need to build a layer which should be compositionally very different than the base substrate, we can do it. Or in other words, on the other extreme, if we want the same alloy to be overlaid on top of an existing substrate for repair job, for reclamation or dimensional restoration, we can even do that. So laser, irrespective of what we are feeding, can melt and create an overlay which could be fairly thick, and in fact it could be much thicker than what is normally possible in case of surface alloying or other approaches. So we can either feed powder, we can feed wire, we can feed a tape, but the difference is in case of alloying, we'll melt the substrate first and then feed the powder or wire into it so that we form an alloyed zone. In case of cladding, we'll melt the clad feed beforehand and allow the molten layer to be incident onto the substrate, and in the process we create a layer which is compositionally very different. But the advantage is because we are overlaying a liquid pool, the liquid actually intermixes well with the substrate and then creates a good bonding with the substrate. So compositionally, the novelty lies in the fact that we actually can create multiple layers with very different compositions and microstructural gradations, which is not necessarily possible in other methods. Process parameter wise, we are talking about the same, the feed rate, apart from the two normal ones, which is the laser power density and the interaction time. Here the composition of the feed and the feed rate also will determine what we create at the finally at the clad zone. The clad zone actually can create a microstructure and phase aggregate which is very different than the normal equilibrium phase aggregate, and this could be to our advantage. But the beauty is that we create a cast layer. Unlike a typical big cast product or a wrought product, the microstructure and the phase aggregates could be very different. So there lies the novelty. And in fact, this is also different than what you can create in terms of laser surface alloying, which I already explained. Laser surface cladding actually is a precursor to the additive manufacturing process. So you can actually build layer by layer and then create a complete structure, a complete component gradually. The the advantage here is that the fusion zone integrates well, so we actually mechanical properties or adhesion properties are much better. So because of the layer that we create, which could be much harder or much more corrosion resistant, we certainly can make a very significant improvement in terms of resistance to wear, corrosion, or any other surface dependent properties. So with this, we actually come to the end of the laser assisted surface engineering processes, and in fact also a discussion on all kinds of surface engineering techniques. So we covered a wide range of techniques, and in the remaining couple of lectures, we'll discuss a little bit about the various real-time situations of components undergoing heavy degradation, and discuss as to what kind of surface engineering technique could be useful for them. So thank you very much.